So we will be starting with the assignment 3. Now, assignment 3, the things are like very formula based, but we will be seeing some theory, okay, some theory before going into this, because in assignment 2, I was unable to finish some of the things. So I'll be finishing those now, okay. So in the last class where we left it here, okay, that we had one conductor in the presence of the north and south pole, and this conductor was being moved. Now when this conductor is being moved, we know that when the conductor is moving and it is in the presence of north and south pole, so what will happen? EMF will be induced across it. So if I mark the polarity of the EMF induced, so how I can find that EMF induced polarity? By using the Fleming's right hand rule. Okay, so here we have okay, एक minute. Okay, somehow this is not coming, whatever I'm writing. Okay, let me just open this once again because somehow what I'm writing is not coming. Okay, so let me open this up quickly. Huh. So here what we have is we have a conductor placed under magnetic poles, and this conductor, you see, this conductor is moving. So what will happen? EMF will get induced. Okay, so EMF will be induced, and then the polarity, where the positive and negative polarity of this EMF induced can be found using the Fleming's right hand rule. Okay, so polarity can be found using Fleming's right hand rule. Okay, so this is the situation. So here if you keep your thumb in the direction of velocity, then you keep your index finger in the direction of your, what you say, this, if you keep your index finger in the direction of magnetic field, so it will be pointing down upwards, because magnetic field is upward from north to south. Okay, like this. Then if you place it like this, so what you will find is, you will find that your current will be going like this. Okay, so it will be like this. So current is going like this, so meaning current is leaving this x, which is positive terminal, and current would have been if if we close this loop somehow, like if we close it by placing some resistance, so what will happen? This current will flow like this, then it will enter this Y terminal, right? So that is why this is a negative terminal. So this is positive terminal, this is negative terminal. Okay. So here if you look at this picture, now in this picture here in the right hand side, okay, what we have is, we have this magnets, like we have put continuous magnets, like this is south pole, then north pole, then south pole, north pole, and this is the top view of this conductor. Okay, so if you look at it from the top, this will be the conductor, and here you can see we have the plus terminal and negative terminal of the conductor marked as per this diagram. This is the same picture, but we have extended this. Like suppose we have like continuous north south pole. Like here we have south pole, then north pole. Then here we had north pole, then south pole, then south pole, north pole, like this. So we have like continuous north pole, south pole, and this conductor is being moved continuously. Okay. So we know that if it is here, when the conductor is at this position, which is the same position as this diagram, which is the north pole below. So I'll draw the other poles. So it is like this. So it is like this. Okay. So, mm, mm. So it is like this, that here you have south pole at the bottom, then north pole at the bottom, south pole at the bottom, and north pole here. Okay, so this is south pole. So it is like this, that at the top, if you have south pole here, if the at the top you have south pole here, then at the bottom you have north pole here. Similarly, if you have at the top north pole, then south pole, then north pole, like this. Okay, so here this region is very similar to the diagram which is shown here. Okay, it is just being shown from other angle, like from the, if you are viewing it from the top. Okay, it is from that angle. So you can see that at the x point we have plus terminal and plus what you say polarity, and at the y terminal we have negative polarity, which we found out using the Fleming's right hand rule. Now, so if we have to write the voltage Vxy, so if I write the voltage Vxy, it will be like this. Okay, so Vxy, you see, so it, because we are writing Vx with respect to y, so x with respect to y is positive at this time. So this is positive. Now, if I place the if now the conductor is moving, so when the conductor is moving, it has now reached at this position. So if the conductor reaches this position, so what will happen is, so this conductor has now reached this position. So here also this is y and this is x. Now in this position you can find, because you see the north and south pole has flipped. Okay, so the south pole has become north pole and north pole has become south pole. So because of this, what will happen, that if you use Fleming's right hand rule, then you will see that this y terminal will now become positive and x terminal will be now become negative. Okay, so if I write Vxy, so Vxy will be negative because terminal is negative with respect to y terminal. So this is negative and then it is positive. So you can see that this is like voltage is continuously like changing like a square wave, right? So first it is positive, then negative, then positive, like this. Okay. We will see things about flux density later. Okay. I'm not bringing in flux density now, but in the coming slides, we will see how the flux density can also be defined. But you understand that this is the voltage is alternating, right, from positive to negative and then negative to positive. Okay, so if we look at this slide. Sakshi, one point. Ha, yes sir. Okay. Explanation previous, right? So here we have not solved. So in an actual machine, like, do we identify this magnets as what? There any reference or how do we? Yes, yes. I'll be discussing just now. You just wait. In the next slides, I'll be discussing, because now in this assignment 3, we'll be discussing that only. Okay. So let me go there. Okay. So this is what is happening. Okay, so here you can see that this, so if we move in this direction, so this polarity changes like this. Now, as pointed out by Abhitej, so we will be seeing how we can extend this discussion to the actual machines. Okay, so let me bring this down. So this is the actual machine, right? Now in the actual machine, what we have is that we have the stator. So this is the stator. Okay, and then we have the rotor. Now in the stator, let us say that we have, like, if suppose it is a, what you say, like a permanent magnet kind of machine. So in the, so we will see that this in the stator we have, suppose for now we will see, let us assume that there is a south pole here and north pole here. Then in the next slides I'll be discussing that how this north and south pole is basically generated in the stator also. Okay, but you see this is the coils now. So this is the rotor coils, let us say the conductors which we were discussing earlier. So these two ends of the conductors we were discussing. Now these two ends of the conductors, we, let us say we have placed it in the rotor. So here also there will be one end and here also there will be one end. Okay, so here also if I what you say, cut this piece here, if suppose let us say I cut this piece here. Okay, so let us say I have cut this piece. So let us say I have cut this place near the north pole. So instead of here, I have cut it here. Okay. So, and if I, what you say, because this is like a, what you say, this is like a cylinder. So if I cut it, then if I, what you say, see it linearly, then I will get it like a plane of sheet like this. Okay. So this is this plane of sheet in which we have North Pole, South Pole, like earlier diagram. Okay. And because this rotor is moving, since this rotor is moving, so it is like this coil is being moved, and then this coil, as per your, what you say, Fleming's right hand rule, it will generate EMF if it is acting as the generator. Okay. Now let us say that how these poles are generated, right? The North Pole and South Pole. So let us say that this terminal is having the polarity as cross, and this terminal is having the polarity as dot. Okay. So we will see this, but here let us see how the south pole is generated. So if I have this terminal as cross and this as dot, so if I use my, what you say, the thing which I discussed earlier, right? If we have to find the flux lines, so what I will do, I will use right hand thumb rule. So what you do, you fold your four fingers in the direction of current. Now you will see that current here, what is happening to the current here? Current is entering the, what you say, cross, right? As I discussed in my first or second lecture, that the cross indicates that current is entering into the plane. So you curl your four fingers in the direction of current entering into the plane, because from here it is coming out and here it is entering, right? So we have to curl our fingers like this. So four fingers should point like this. Then your thumb will indicate the direction of the magnetic field, right? So this is how you will see your hand if you use right hand thumb rule. So now if you see your thumb is pointing upwards, so it means that the field lines are going upwards. So field lines are going upwards means it is entering this supposedly pole. So in which pole the flux line enters? We know that the flux line leaves the north pole and flux lines enters the south pole, right? So in this way we have determined that, okay, if I need to get a south pole, then what I'll do is I will place the coils in such a way that it will be wound in this. So here it is like this, so we can wound our coils like this. Okay. And by using some mechanism we can pass the current in this way, so that the flux lines are generated in the upward direction, means that the flux lines are entering this. So flux lines are entering this means it acts as the south pole. Okay. Now coming to the north pole, now for, if I suppose, okay, if I did not want the south pole here, I want the north pole at the same position, then what I will do is I will just flip this direction of current. So instead of passing the current like this, so instead of passing the currents like this, okay, I will pass the current in the opposite direction. So what I will do, I will if I do like this, so I will pass the current in the opposite direction. So you will see that the current is basic, what is happening to the current. So if you again use your right hand thumb rule, so in this case you will see that your thumb, because you are, it here it is what, here it is dot and here it is cross. Okay, so because here it is dot, so your current is coming out of the plane or the your copy or computer screen, and cross means current is entering the computer screen. So if I place my right hand like this, so how it will happen? It will be happening something like this. Okay, so you will see that your right hand, your thumbs, your fingers will be like this. Okay, and the thumb will be pointing downwards. So it means what? This is acting as the north pole, because your flux lines are going away, right? They are going away. So here if you see the if the flux lines are going away, then this means that this pole is north pole, and if the flux lines are entering, this pole is acting as the south pole. So in an actual machine, by properly putting the, what you say, by properly putting the coils, you can control whether some pole is acting as the north pole or acting as the south pole, basically like an electromagnet. Okay, so as we will be discussing the machines, you will see that in the DC machines, this is how the poles are generated. So this is similar to DC machine. In DC machines, exactly this is how the poles are generated. Okay, now we will when we will see induction machine and synchronous machines, slowly we will see that how by various means we can generate the, what you say, magnetic field. Okay, what is the nature of magnetic field, whether the magnetic field is stationary or whether the magnetic field is rotating. Here you can see that in the DC machine, in this kind of structure, where we have put this kind of conduct like DC current, like if we what you say, make the DC current to flow like this. Okay, and here also like this. So you will see that this, because these poles will become stationary in space. Okay, so these poles will be stationary. So for DC machines, as the name suggests, okay, name suggests means the name suggests what will be the nature of the armature current by using commutator arrangement. But here I want to say that in DC machines, what happens, you use electromagnets. Okay, in stator to produce stationary poles in this way. Okay. Now coming to the rotor, now in the similar fashion, if you see, here we have cross and here we have dot. Now if you apply your right hand thumb rule, then what will your right hand thumb rule will say? If you curl your four fingers in the direction in which the your four fingers are what you say, entering the plane and coming out from this direction, so you will see that your four fingers will be something like this. Okay. So it is like this, and then your thumb will be like this. Okay, so you will see that if you place your right hand thumb, if you apply right hand thumb rule for this kind of coil for the rotors, like, because in the rotor also the coils will have some EMF induced. So this, if we suppose this kind of EMF is induced, then what will happen that your so here this side, because this side is your flux lines are leaving from this side, so this will act as the north pole of the rotor. And here, if you extend this, so flux lines have to enter through here, so this will act as the south pole of the rotor. Okay, so this is how you can see. Now in generator the EMF is induced, but if we talk about motor, now in the motor, what you do in the motor, you pass the current in the, what you say, rotor coils. So in this rotor coils, you have made the currents to be passed in such a way that the cross is here and the dot is here. So because of this cross and dot notation, your north and south pole of the rotors will be like this. Okay, in the similar way how we have what you say, found the north and south pole in the stator. Okay, now in this diagram, so this is about the north and south pole, how the north and south pole are generated in the machine. Like, this is one example. So as I was saying, that if you cut this here, like suppose if you cut your this cross section here, and you what you say linearly you try to see your this machine. So if you place this linearly, so you will see that this is like an alternating north and south pole, and here you have the conductor, and because this rotor is moving, so this conductor is also moving in this direction, right? It is moving in this direction. So it is very similar to your this example, right? So we can extend our knowledge from this linear system to the rotating system in this way, by thinking, okay, if what will happen if I extend this by cutting it here, so I will get this kind of structure only, which is similar to the linear system. Okay, now going further, now we have to see how the torque is, what you say, obtained in your rotating machines. What is the general principle? Okay, so let us see how the torque is produced. So these
Sakshi, one more point. Sorry.
Hmm.
In case of permanent magnets, when we do the magnetization, do they recognize as a north and south for the magnets, or is it that automatically by dipole phenomena it takes the north and south?
Yes, actually in permanent magnets, because you see this is that is not an electromagnet, right? So what happens is that it is already like polarized in a way, like it is in the factories and all. What they do is they align the dipoles in such a way that the north and south poles are already formed, identified. But if you're using electromagnets, like suppose your DC machines, if you use permanent magnets, it's okay. But in generally most of the cases, you will see that we use electromagnets because permanent magnets are rare earth metals, right? So they are costly. So you will see that in places where you can use electromagnets, this is how your what you say poles are generally formed in this way. Okay. Okay.
And while magnetizing, say in the permanent magnet, you have both the surfaces. So will this magnetization happens both faces? Any idea on this, or is it that only one face it happens?
You're talking about permanent magnets only? Actually, I do not know much about it, so you can just find some literature. Okay.
Yeah,
Hmm.
fine.
Ha ha. Okay. Okay. So, yes. So, as said that you can also use permanent magnets also instead of electromagnets, but the thing is that the permanent magnets require rare earth metals. So, in most of the cases, you will see that we have to use electromagnets. In very special cases, like suppose you cannot do lot of maintenance or something, like because if you will see that if you use permanent magnets machine, they are generally what you say smaller in size, okay, compared to your electromagnets configuration. So if you have like space constraints, if you have maintenance constraints, like your machine is located in such a location where you cannot do too much maintenance, then in such special cases only that generally permanent magnets are used. But in most of the industrial cases we use electromagnets only. Okay. So, coming back to our discussion here, um, so here, let us come back here. So here, as I was saying, that we will be discussing the basic principle of how the electrical machine is of rotating action is obtained in the motors. Okay, so let us see how it is obtained. So let us take the case of induction generator. Okay, so induction motor. So this is the case of induction motor. So in the case of induction motor, so as I said that what will happen, so let us say that at given point of time, we have the south pole of the stator here, north pole of the state. So let us say it, we are starting like this. So here let us say that the south pole of the stator is here, the north pole of the stator is here. Okay, because stator is fixed. Okay, so stator means that the part of the electrical machine which is fixed, and rotor means, as the name suggests, it can rotate. Okay, rotating part. So here if you see, this is the stator, so this is the stator and this is the in the stator we have the poles. Now let us say this is the south pole of the stator and north pole of the stator. Now the rotor, let us say that at given point of time you have passed the currents in the coil, and by passing the currents in the coil you have got, suppose let us say, north and south pole in this fashion, like north pole you have obtained here and south pole you have obtained here. Now what will happen, that due to the what you say magnetic principle, what will happen, this south pole of the rotor will get attracted towards the north pole of the stator, and this north pole of the rotor will get attracted toward the south pole of the stator. So in this way what will happen, the machine will experience a torque in this direction, right? But what will happen, so in this way the machine will have some initial torque, so it will rotate in this anti-clockwise direction. But after some point you may think that, okay, what will happen if this south pole of the rotor has reached the north pole of the stator, and this north pole of the rotor has reached the south pole of the stator. So after this, so there should be no more motion, right? So that is why you will see, for getting this rotating motion, generally what we do is that in induction machine, so you will see that in induction machine, I think the sir will discuss this in the later classes, but I'm just giving you one something, so that you will not be completely clueless. Okay, so in induction machine what we have is that we have, so let me write. So in induction machine, okay, in the stator, so in the stator we have, okay, uh, three phase windings which are distributed in space. This is for induction, or you can say synchronous machine also. Okay, distributed in space, like in general principle of rotating machine, I'm saying. Okay, so because we have the three phase windings distributed in space, so what you have is that you have something like this. Okay, so we have, suppose, A dash, A, okay, B, okay, this is not B, this is C. So let us use like some conventional colors for the three faces, so that you will understand that these are three faces, okay? Which I'm three phase windings which I'm distributing in space. So let me call it as R and R dash only. So this is, say, R dash, R. Let us say it is having cross. This is having dot. Okay. Then Y phase. So Y phase you have here. So here you have Y phase is here. Okay, let me draw other B phase also. Then I'll say. Mm, this is the B phase. Okay, so here the B phase is like this, that you have, okay, so let us say it is like this, that you have three phases which are distributed in space. Okay, so what happens that if in these three phase windings, like there are three phases distributed in space, so you will see that in the state, in the machine we have like this, that you have the stator. Okay, so in the stator you will have some stator slots. Okay, so in the stator you will, suppose I'm in the stator, you have slots like this. Okay, I hope you get the idea. Like this we have the slots. So here I am representing a concentrated view. Here they are distributed. Distributed means that in each of the slots you have some R, Y, B windings. So it is like this. So this is one slot. So I'm drawing one slot for example. Okay. So in one slot you have some R phase what you say conductors. So you have some R phase conductors. Let us say you have three R phase conductors. Okay. Then let us say two Y phase conductors and one B phase conductors. Okay. This is like distributed so that they are like sinusoidally distributed in space. I hope you understand that if you what you say if you see this, if you see the flux by these windings, we will see how you can see the flux enclosed by, if suppose there are some number of um, what you say conductors which are placed in a slot, then we will see that how the flux lines are produced. Okay, so you will see that because of the R phase there will be some flux line which will be like approximately sinusoidal in space, and due to Y phase also there will be some flux lines which will be like sinusoidal in space. So this is like this. Okay, so you will understand what I'm discussing about this sinusoidal distribution in space. Actually this is little bit too early to discuss these things will be coming in the later assignments, but so that it should not be like what is happening, how the what you say stator um so it is like this. Okay, so the ry b phase they are all sinusoidal fluxes, so I am writing it as b. So what will happen that you have three phase windings which are distributed in space. So if suppose in these three phase windings if you put dc currents, so what will happen, due to this dc current there will be like this sinusoid distribution, but you will not be passing the dc current in this three phase windings, right? So you will be passing the what you say three phase balanced system, right? So it will be like this, that you will be passing and which are distributed in space, and these windings, okay, so and these windings are carrying current which are distributed in time. Okay, so you will see that how the number how we can place the conductors in such a way that we get sinusoidal distribution in space. Okay, but you give them, but you give three phase currents like this, so you have three kinds of sinusoidal distribution. One is in space due to by placing the number of windings, and one is in time. In time means you are giving the three phase currents like this. Let us say you are giving currents like this, I is equal to ia sine omega t, which is distributed in time because omega t. Okay, ia, let us say ib is im sine omega t minus 120, and ic is im sine omega t plus 120. So because of this you will see that what will happen, that there will be a magnetic field which will be produced. Okay, so if we will see in the later classes that that magnetic field, if you find out that mmf due to that, so if you do the mmf of you try to find the mmf of this, you will see that this will come out to be something like this. Okay, so 3 by 2 ns im sine omega t minus theta, where theta is the space angle and omega t is the time angle. Okay, so you will see that this mmf is basically what it is having some fixed magnitude, but it is rotating in space. Okay, so in this way you can have the north and south poles which are rotating in space. Okay, so what will happen, because you have made it such that your, so what will happen that south and north pole is continuously rotating of the stator, so stator is continuously rotating like this, and this south and north pole of this rotor is chasing this stator north and south pole. Okay, so in this way there is continuous motion, that the north and south, so the poles in stator are rotating. Okay, I know this is too much discussion at this point of time, because this is like, maybe it will be discussed in some assignment 5 6 like that. Okay, but I just discussed, you don't have, if you do not get it right now, it is okay. But for some people who already know this, they will understand what I'm talking about. But if you do not understand at this point of time, no need to worry. But just think that if the poles in the stator are rotating, so what will happen? These rotor poles will also try to chase these stator poles which are rotating, right? So these rotor poles, okay, will chase the stator poles. Okay. So in this way, what will happen? That rotor will rotate continuously, and because of this, there will be rotating motion. Okay. So you see that relative. So what will happen, that the because of this magnetic attraction, this relative speed will be zero, because they are moving at constant speed. However, because there is rotation in the rotor, that rotation is due to this electromagnetic torque which is produced due to this magnet action. Okay. So this down part is extra. Okay, this top part, if you understand at this point of time, it is more than enough. Okay, we will be discussing these things again later in the class. Just discussed it right now briefly. Okay, don't worry if you do not get it right now, but you understand that in this way you can make your stator poles to rotate, and because of this magnetic action, this north poles will chase the this rotor poles will chase the stator poles. So due to this magnetic action, there is this a torque produced, due to which this rotor rotates. Okay. So here, this is one example. Like here, these are the north and south poles. So another thing is that the north and south poles of the rotor and stators must be equal. Okay. So the number of poles in the stator and rotor must be exactly equal. Okay, so here there is it is shown that how you can create the four poles. Like in the earlier example, we have seen two poles. Here you can create four poles in the stator by keeping the coils like this. As I've discussed, this you can get by using the right hand thumb rule. So here you can place the uh, so so here so instead here we were getting the, what you say, two coils, right? By placing the, what you say, coils like this. So if suppose you place the coils around the coils also, there will be some north and south poles, right, in the rotor. So I hope you get the idea how to get the poles in the what you say, stator. Okay, by using this right hand thumb rule you can get it. Okay. So this is some slide which sir was discussing, that how by connecting these coils in series you can get the EMF. So if suppose you have like two turns, so in the two turns, someone has come, so let me admit this person. Okay. So this is one slide which is not that relevant slide. He was discussing this not for for solving assignment. This is not very relevant slide. Okay. So but you must remember that the number of poles in the stator and rotor must be exactly equal. Okay. So why it should be equal? So let us see this here. So here what we have is that we have the north and south pole in the stator. Then if suppose you have two poles in the stator but you have four poles in the rotor, then what will happen? This south pole of the rotor will experience force in this direction, because it will get attracted towards this north pole of the stator. This north pole will face repulsion from this north pole of the stator, so it will try to move over here. But here also, this, due to this south pole, this south pole of the rotor will experience force in this direction, and this north pole will come here. So you can see that some of the forces are in the anti-clockwise direction, some of the forces are in the clockwise direction. So what will happen? The overall forces will cancel out and this rotor will not move at all. That is why it is very important that the number of poles in the stator and rotor must be exactly equal. Okay. So coming here, so this is an example of DC machine. Now in DC machine, what we do is that here that we have this, so here what we are having stator field lines like this from north to south. So it is from left hand side to right hand side. We can see that this is the field of the stator Fs. Okay. Now, in the DC machine, what you do by using the commutator arrangement, what you do is so what will happen that one set of conductors which are under the north pole will always have one polarity of the current direction, and another set of the conductors which are under the south pole will always have one particular polarity of current direction by using the commutator arrangement. Okay, so in DC machines, so I'm just writing it down. So in DC machines, um, set of conductors under North Pole or South Pole will have a particular um, direction. Okay, we'll have a set particular. I said, I think it is from particular, the set word is more accurate. Okay, we'll have a set direction by using commutators. Okay, so what will happen? So if you try to find the direction of force by using the Fleming's left hand rule, so if how you will find the direction? So you what you will do, you will align your, so first of all we'll know that because of if suppose it is like this that sorry. Okay, so let us say these conductors are having dot current and these conductors are having cross current. So very interestingly, you can find the direction of this rotation in two ways. Okay, so I will tell one way we know by using the Fleming's left hand rule. Okay, so by using Fleming's left hand rule, if you so this is the um, north and south pole of the stator. So this is NS SS. So here you put your if you put your fingers in proper way, so here how you will put your left hand uh, index finger in the direction of the field. Okay, and your what you say, this middle finger of the left hand in the direction of current. So current is coming out of the plane. Okay, so you will see that it will be something like this, and then your thumb is like this. Okay, so this is how is your um okay, so this is how your left hand will be. So you will see that your thumb is pointing upwards. Upwards means it is trying to rotate in this direction. Okay, so it is here on this side, it is this direction, means it is in this direction. Now interestingly, another way to find out is that first of all you can try to find out that due to these conductors which are placed, what is the north and south pole of the rotor. So you will you if by using the, so this is Fleming's left hand rule, and Let us say uh, right hand thumb rule. Now, right hand thumb rule, what you will do, you will curl your right hand forefingers in such a way that your forefingers enter the, what you say, your, so it the your right hand finger should come out from the left hand, from their left side, and it should enter from the right side. So it will be something like this. Okay. So this is how your fingers will be. Okay. So you will see that the thumb is pointing upwards. So it means what? So this is coming out. So from the rotor it is coming out, means from this point it is acting as the north pole, and this point it is acting as the south pole, right? Because field lines are pointing upwards for the for the rotor. So from the rotor it is leaving, so it means that this point of the rotor is acting as the north pole. So because the field lines are leaving here, so what will happen, this north pole of the rotor will get attracted toward the south pole in this direction, and south pole of the rotor will get attracted towards the north pole in this direction, right? So what will happen that this direction, so we can find the, what you say, direction of rotation by using the right hand thumb rule also. Okay, so we can get the direction of rotation using the Fleming's left hand rule and also using right hand rule. So you will see that both of them are pointing in this clockwise direction. Now, but because this is a DC machine, so what will happen, even if this rotation happens, so but again this conductors, suppose this conductor comes here, but as soon as this conductor comes from cross to dot, so what will happen is that because of the commutator, the current will become from cross to dot. Okay, from, if it is, this conductor is moving from south pole to north pole, because of the commutator action, because under north pole, it should have only one particular direction of current, which is dot. So what will happen, this cross will become dot. But so what will happen, there will be continuous rotation. Okay, so here you will see that the, because of the commutator action, there is a continuous rotation in the DC machine. Okay, this is something which sir discussed, that is why I also discussed. Okay, so that if suppose some theoretical questions comes, you can answer. Now, as I was saying, how to find the so here we discussed how the voltage is induced. Now we will try to see how the how the, what you say, MMF or the flux density can graph can be achieved. Okay, so let us see here. Okay, so okay, so see very carefully. Okay, so I'm not writing again and again because I have just taken this from the sir's lectures directly, so that I will discuss this and it will save the time which will be required for writing things down, so that I can discuss maximum things possible. Okay, so here you see we have the conductor, right? We are talking about only suppose say one conductor. Let us for now focus on only one conductor. So we have one end of the conductor here and another end of the conductor here. Okay, or like what we do is that so basically in the, so this is a coil. Okay, so in my last class I discussed something called as coil. Now we have come out from the linear to the rotating part. So now I'll be discussing about the coil and on coil span, all these things. Okay, so here what we do is that we have a, so at this place and this place. Okay, so let us say this is north pole, this is south pole. So here we have one end of the coil. Okay, like this, and for each coil we have two conductors. Okay, if it is one turn coil, remember. Okay, and this width I have discussed earlier. Okay, this width is a coil span, also pole pitch. Now, for maximum EMF induced, this coil span should equal the pole pitch. Okay. So if one end of the coil is placed under north pole and one end of the coil is placed in the south pole, in that condition you will get the maximum, what you say, EMF induced. Okay. So this is equal to 180-degree electrical. Okay. So these things are already discussed by sir. I've just written this down. So I hope you understand that here what we have is that this is the same picture. So here we have one end of the coil here and the other end of the coil here. Okay. So what will happen that we will now try to see what is the MMF induced. So as per the Ampere's law, what does Ampere's law say? It says that this closed contour integration of the HDL equal to the current enclosed. So if suppose you draw a closed contour around this conduct this what you say, this coil end, so you will see that what is the how much, what is the amount of current which is getting enclosed. So it is in one direction. Okay. So in similarly you will see that if from using this this law we can find that so in this direction, in this time, only one set of coil is getting in, what you say, one end of the coil is getting enclosed. That is why MMF was in one direction. But as soon as we reach this conductor, so because now if we draw a contour here, so if we draw a contour here, so what will happen, we have now seen, okay, this direction is reversing, because from this contour to this contour, this MMF direction is opposite. You can see that because the current here is dot, so current here is dot means by using the right hand thumb rule, you will see that this is the flux lines. Okay. But here, because this is cross, so you will see this is how the flux lines are. So what is happening? The direction of flux lines is changing. That is why the direction of this MMF or flux density is also changing like this. Okay. So for a DC, so if suppose you have only two conductors, so you will get this kind of a DC MMF. Okay. Now, if suppose we place our so let us now talk about the stator coils. Okay. So let us say we have one here. This is 1 dash, 2, 2 dash. Okay. So we have cross, cross, dot, dot. Okay. So what will happen? So due to 1 and 1 dash, so let us say this is 1, 1 dash. So we will have MMF like this. Okay. So, and due to 2 and 2 dash, you will have MMF like this. Okay. So what will happen if you sum this up, you will get something like this. Okay. Then it is only single is there, then it is zero, something like this. Okay. So if you increase the number of steps, okay, if you have more number of conductors, and by placing how many number of conductors are there. Like if suppose it is having like, so if you have equal number of conductors, you, and if you have multiple number of conductors, you will get something like this steps, right? But if by controlling how many number of turns you are placing inside the conductor, you can also design how much height is this. If the number of turns or number of conductors in us all in all the slots are equal, then what will happen, this will have what you say, exactly equal number of steps, exactly equal height of steps, okay, exactly equal height of steps. But this height also you can vary by deciding if how many number of conductors or coils you are placing under this slot, okay. By varying this, you can approach to a sinusoidal distribution, okay. So you can approach sinusoidal distribution. That is why in our all discussions from now onwards, we will be taking that the flux, okay, flux in the stator coils are what you say, sinusoidal, okay. Or in the rotor also, if suppose in the rotor you have what you said distributed windings, like if in synchronous machine if you have like non-salient pole, like all distributed windings, then in stator or rotor flux lines you will get sinusoidal distribution, okay. So I hope this you understand. So if you have any doubt at any point of time, I know I'm discussing very many things, but if you have any doubt, please ask. Okay. It's these are very heavy things, I understand, but I'm discussing it so that you can understand the theory also behind this electrical machine, this course. Okay. So this is how you get sinusoidal distribution. Now we will derive the expression of EMF voltage. Okay. So let us now see that. So here you will see that first of all, what is the velocity in meter per second? If suppose let us say we are saying that n is the number of rotations per sec, n is the number of rotations per second, also written as RPS. Okay. So what will be the velocity in meter per second? We have to find. So how we can find? So how we will find is that 1 second. Hmm. So let us say that in one, so we know that our diameter of this rotor, so this rotor is there. Sorry. So this diameter is d in meters. Okay, so this is d in meters is the diameter of rotor. Okay, so these in this. So if we have to find the, so what will be the distance which will be covered in 1 second? So let us see. Okay, so we know that if we say that in one rotation, so what will be the distance in one full rotation? So the distance in one full rotation will be pi into d or 2 pi r circumference. But in 1 second, how many rotations we are making? We are making small n rotations. So instead of this 2 pi r, we are saying that okay, but we are claiming that in 1 second we have also made n, we have made the rotations n times, small n times. So what will happen? So this in if I have to write the speed, so it will be pi dn meter per second, because in 1 second we are moving pi dn meters. Okay, so this is how you can find velocity in meter per second. Okay, and omega, we know omega is 2 pi n, or omega, this is radian per second, or 2 pi capital N, where n, capital N is in RPM, by 60 radian per second. Okay. So here sir has written various things. So first of all, we know that okay, that what will be the EMF induced in a conductor. So we know that so let me just draw again. Okay, so let me draw it somewhere here. Okay. Okay, this is blocking the view, right? Right. Okay. So here let us now try to see. So we know that the in a coil there are two conductors, right? So for one conductor, what is the EMF induced? EMF induced for one conductor is BLV, which we have seen from the last class. But there are two conductors in a coil, that is why there is a two term, 2 BLV. Okay, 2 for two conductors in a coil. Okay, equals to 2 BLV. Now we know that B is sinusoidal. So B is, let me write it as small b because it is instantaneous value. So EMF will be 2 um, B max sine theta LV. Okay, where V is in velocity in meter per second. Because we have converted everything in what you say SI units so that we can get EMF induced in volts. Okay, so that is why it is like this. Now, another thing is that what is this N, capital N? So this capital N means your what you say number of turns. So if suppose there is only single turn coil, so this is a single turn coil. But if suppose it is a multi-turn coil having n number, capital N number of turns, so if suppose it is having two turns, so two turns means how many conductors it will have? Okay, so it will have 2 into 2, 4 conductors, right? Two turn coil, two turn coil. So if multi-turn coil with n, capital N as multi-turn coil having capital N number of turns. So in this way, we have to multiply capital N also. Okay, so this is the expression of your EMF. But you will see that this is the basic expression of EMF. Okay, but here, so V is in meter per second. But if you want, if suppose your information is given in what you say, because generally the information of speed will not be given in meter per second, right? It will be given either in radian per second, RPM or RPS. Most generally in cases it is given in the form of RPM or RPS. Okay, so I am just replacing, you can replace this small v with RPM, okay, or RPS. So sir has replaced it with RPS, so we will be following the same thing. L pi dn sine theta. Okay, which we have obtained that pi dn is the um pi d small n is the what you say, where n is the speed in RPS, so we can replace v with pi dn. So this is the expression of EMF. But this is the very basic expression of EMF. This expression of EMF lacks the information of uh, this is not the expression which we generally see, right? So we will be deriving. So I am not deriving this. I am just telling you the expression. So before that, we will see flux per pole. Okay. So in this above expression, if we replace this B max this with the flux per pole, we can find the expression. Okay. So I'm not deriving this because this derivation is big. You can just see sir's lecture. Sir has derived it very nicely. So you can see that. Okay. So here you will see that this is the expression of the EMF. This is very important. Okay. So this is very important. Okay. This is very important. So you will see it like this. 4.44. This root 2 pi is 4.44. FIN in your notebooks, in your BTech or some in the literature you will see it as 4.44 root 2 pi replaced. So this is a very basic expression of EMF. This derivation is discussed by sir. Okay, I'm not discussing it. So it's not very what you said difficult derivation. You can see and understand it. Okay, I was having because I have to discuss questions also, right? So that is why I did not. I'm not writing the derivation here and explaining it. Okay, but it is this it's just maths. You can also understand. It's not having any concept as such. Okay, so you see here, so now we have to derive the what is the flux per pole, right? So we have to so we will so here in his expressions, what will sir do is sir will replace wherever is the bmax with this what you say flux per pole phi. Okay, so by replacing this with phi, and by what you say converting this small n also in terms of what you say frequency, he has derived this expression. Okay, so I am discussing the phi part. So the frequency part is simple. Okay, you can understand very easily. So here, because in the questions they will ask you flux per pole to find it separately also, so I will just discuss its derivation. So here you see that here what we have to find flux per pole. So what is the flux per pole? So first of all, we know that flux density is what, flux upon area, but we are trying to find what, we are trying to find flux per pole. So what we will do is we will multiply the flux density with the area. But what is the area? So you see in the rotor, this is the what you say. So if we have to find the area, so this is the area which the flux is passing, right? The flux is passing this area. So what will happen, that so we have to find the area, this area. So what is this area? We know from our mass that this arc length is r into d theta. So this is d theta and this is r. So r into d theta is d by 2 r into d theta. This is d theta. And this length of this rotor, because this rotor is like it's not circular, right? It is cylindrical. So that cylindrical height or length is L. So that is why we are multiplying this r d theta with this L, so that we can find this area. So this arc length into this length of the rotor will give you this area. So this is the thing. But understand that this d theta is what? Is electrical angle. Theta, wherever we have discussed, it is electrical angle. Okay, this sine theta also is electrical angle. Theta in terms of electrical angle. So what we will do? We will replace this with the mechanical angle. So what is the relation between the electrical and mechanical angle? Theta is p by 2, theta mechanical. So theta mechanical will be 2 theta by p. So that is why 2 by p we have multiplied, so that we get this flux d phi as this. Now we have to integrate it over one cycle. So if we, so because it is repeating every half cycle, so if we integrate it from 0 to pi, it is we can, because see what is under one pole, what is the electrical degrees. So we have discussed that so one so let, where I have discussed somewhere na uh, एक minute. So here you see, you will see that this one pole, under one pole, you will see that 180 degrees are electrical degrees are there. Okay. So what we are doing, we are trying to integrate over that. So if we integrate this theta over 0 to pi, because under one pole there are 180 degree electrical. So if we integrate that, we will get the value of phi as this. Okay. So you will see that we will be using this value of phi in some of the questions where it is asked to find the flux per pole. Okay. So this is the value, you can see we it has been derived. So if you replace this if this bmax with in terms of phi in this expression, and if you replace this small n in terms of your frequency, then you will see that this you will get obtain this expression. Okay, so you just remember this expression and this expression for solving the numericals. So now you will see that there is something called as distribution factor and there is something called as pitch factor. Now why this distribution factor and pitch factor comes into picture is that sometimes your EMF is not exactly this root 2 pi 4.44 f phi n. Okay, why? Because sometimes what will happen that instead of this 0 to 180 degree, you may not keep your you may not keep your coil like this. You may not keep your whole this coil over a 180 degree. Sometimes you may keep it on 160 degree only, like you may place it in some other slot here. So we call that as short pitched. Full pitched means that the coil is placed over 180 degree when your coil span is equal to pole pitch and you get maximum EMF induced. But instead, if you keep it like suppose 1 2 slots before, then it is called as okay, this coil, this is a short pitched coil, okay, or short pitched winding. It means that you are missing the full pitch by some number of coils, number of slots, okay. So that is, in that case, you will see that we will have something called as pitch factor. So I will give the formula of pitch factor when we are solving the question only. I have not written that down. And there is something called as distribution factor. Now how come this distribution factor comes into picture? Because this so if you will see the EMFs in the across the conductors, so you see, so you will see that these conductors EMF, if you try to find out, they're not exactly algebraic sum. Okay, if they're algebraic sum, then if suppose you have two E like this, okay, so if they're algebraic sum, then you will get exactly 2E. But instead, what we have is we have vector sum of the conductor. So what will you will get? You will get something less than 2E. So to take care of that, we have something called as distribution factor. So you please remember this distribution factor formula also. Okay. So beta, generally we will see that beta is what you say, angle between two consecutive slots. So how you can find angle between two consecutive slots? So beta is angle between two consecutive slots. Okay. So beta, you will see that we know that total number of slots divided by number of poles will give you slots per pole. So we know that these number of slots per pole has 180 degree, unless it is specified it is short pitched or something. Okay. So if it is 180 degree, then you will see that okay, if it is 180 degree, then you know that so suppose let us say, so let us take this example. Okay, so sir has said that okay, let us say you have a 4 pole machine with 24 slots. So what is the slots per pole? You have 24 by 4, 6 slots per pole. We know that one pole has 180 degree. So what is the angle between two consecutive slots in the pole? So 6 slots have 180 degree. So one slot will have 180 degree by 6, which is 30 degrees. So one slot between two consecutive slot or one slot angle will be 30 degree. So beta is 30 degree. But you see this so here this is beta electrical, remember, because 180 degree is electrical angle, electrical degrees, right? So like this you can find beta, and we will see in the assignment question how we can find the M. Okay, so you will see how we can find M. So let us now see the questions. Okay. So here the question is that a 6 pole, so this is the common data for the questions. So in this common data, what is given is that a 6 pole 3 phase 60 hertz generator, okay, has an active length of L is equal to 0.5 meter, diameter as this much, 54 slots, 60 degree phase spread double layer winding. Assume air gap flux density to be sinusoidal with Bmax this much. Coils have 6 turns each and are short pitched by 2 slots. So first of all, they're asking how many coils does the stator have. Okay, so this I discussed in my last class, but I will again show it to you for people did not see that. Okay, So in the last class, as I was saying, that what happens that if suppose for a double layer binding means that you can have, it can accommodate two ends of the coils in a one slot. So you see in each of the slots you can accommodate two ends. So if suppose this is the starting end, so and it will end somewhere, but then again it is starting from something and then it is ending here. So you will see in this kind of double layer binding, the number of coils is equal to number of slots. Okay, for double layer binding. So for double layer binding, number of coils is equal to number of slots. And for single layer binding, number of what you say number of coils is equal to number of slots by 2. So if you come back here, this is a double layer binding. So for a double layer binding, number of coils is equal to number of slots, which is equal to 54. Okay, so the answer of this question is 54. If it were single layer binding, then it would have been 54 by 2. So 54 number of slots by 2, 54 by 2. Okay, in that case. It is a simple question. You just have to remember this structure. Now, in the next question, actually, they should have mentioned some other value, but uh, they have mentioned some other thing. Okay, I'll discuss. So they are saying that the slots are numbered from 1 to 54 because there are 54 number of slots. So each slot is having some number. So they are saying that one side of a particular coil is in slot number 2. If the other side of that coil is not in slot number 9, then in which slot it is? It should be. Okay. So we know what? So first of all, this is a short corded by two slots. So short. So first of all, we know that how many slots per pole. So we can find the slots per pole as 54 by 6, which is 9. So this is 9 slots per pole. Okay. So under a pole, there are 9 slots. Now, but what has happened? It has happened is such that you have something like this. That 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay. So it is like this. So here, this is like North Pole. And let us say this is South Pole. Okay. So this is 1, 2, 3, 4, 5, 6, 7, 8. So there are 9 slots, right? So this has to be 9 should also be under North Pole. Okay, so under normal conditions, what should have happened is that if suppose this is a coil, so I'm drawing the coil down. So one end of the coil should have been in 1 and one end of the coil should have been at 10. But they are saying that instead of keeping it at 10, because this is short corded by two slots, so it is kept instead in this. Okay. So it is like this. So 1 plus 9 minus 2, which is how much? 9 minus 8, which so it will be in 8. So this is called as short pitched. Okay. Short pitched or short corded. Okay. So now they're saying that okay, so suppose there is the one coil is in number 2. So where this should number 2 end should be, the other end of the number 2 where it should be. Okay. So let us try to find out then. So they are saying, so how we can find? We can just find it out like this. So how so it is like this, that 2 plus 9. Mine, how come they have written it like this? Let me just see. I think they have made some mistake. Okay. So it is very simple. It should have given you the answer as 9. So two second one should have been in the 7. So second one, 2, No, second one should not be in the 7, right? 2 plus 9 minus 2. I think there is some problem in this question. Okay. I think they have given this wrong, but you understand, right? So if it were 1, then it would have been something like this, that 1 plus 9 minus 2. 10 minus 2 means it would have been in the 8th. Now this 2 1 should be in the ninth one, right? So 2 1 should be in the ninth one, like this. So they are saying if the other side of that coil is not in the slot number 9. So they're clearly saying that this is not in slot number 9. Their solution is wrong. Okay, don't see this solution. This is not correct. Then then other end of the coil should be before it. So let us now try to see. So this is 1. So we will now draw it backwards. Okay. So this is 54, 53, 52, 51, 50, 49. So now let us now try to find. So if we have to go back, so how what is the distance? So 2 to 9. So we have to maintain 7, right? So 7, we have to go back 7. So this is like 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7. So it has to come to 49. Okay, like this. So correct answer is 49, but what they're trying to say here, I'm not understanding. Okay. So I hope you understand this. This one you understand. I think this one they are trying to this one is still okay because they are just thinking that okay, if it is subtracting, then you are subtract what you say, doing it from the 54 side. Okay, so whatever is the negative number you are getting, if you add to 54, I think you will get 49. But this one, what they're trying to say, this is this is wrong. Okay, so I hope this is very simple question. You just have to understand this structure, geometry. Okay. Now, here you have to find this, what is the slot pitch. Okay, so how you will find the slot pitch? You will just find the 180 degrees, the so slots per pole. So how many slots per pole? So slots per pole is 9. Now, under normal conditions, if suppose it was not short corded, so you see, you will think that okay, but it is short corded. How you are saying that the whole 180 degree is under the 9, right? It should be under the under the what you say 7. But you try to understand, we generally say pole pitch as the pole. We define it as per the pole. We did not define it as per where we are placing the coil. Okay, the pole pitch definition itself is that the number of slots which are under the pole, the number of slots under the pole does not change. Okay, so you will see that the number of slots under the pole is not changing. For, as per the machine geometry, it will be the same. But what we are changing it, instead of placing it full winding, we are placing it somewhere before it. Okay, that is our decision, but it does not change the geometry of the machine or geometry of the pole. That is why slots per pole is still 9, and the slot pitch, which is the angle of each slot, that also remains the same. Okay, it does not change by changing the short corded. For taking care of the short corded thing, we have something called as pitch factor. Okay, that you don't worry. So we know that 180 degree electrical, so 9 slots have 180 degree electrical. So one slot will have 180 degree by 9, 20 degree electrical. Now you please read the question carefully whether they are asking electrical degrees or mechanical degrees. Okay, here they are asking electrical degrees, so that is sufficient for us. Now we have to find the rated speed in RPM. So we know the formula, very famous formula. So N in RPM is 120 F by P. Okay, so this is the relation between the RPM and the frequency. So in this expression, we can place the what you say this here, this r, we had rps, right? Small n in rps. And what is the relation between rps and rpm? So n is equal to capital N by 60. Okay, so this is the thing. So by using this, so by replacing these things, we have obtained the expression, okay, here. But you remember this n and this capital N, I want, I mean is this is n rpm, okay, n rpm. So coming to this question, so here you will see that if you relate it properly, you will get this relation, okay, between the, so here you will get it as this I think sir has derived, okay, where this derivation is discussed in this lecture, where this derivation of pole pitch is discussed. After that only he has derived the expression of between relation between the frequency and rps or rpm, okay, you can see that. So from there you will get this formula. So in this formula, you just place the frequency. So if you place the frequency 60 and number of poles as 6, so here if you do that, so you will get it as 1200 rpm. Okay, this is very simple. Now we have to find the value of flux per pole. So we have derived the flux per pole, right? The derivation, we have seen the flux per pole. So what is the formula of flux per pole? So what is given? They have given diameter. So we have to take the formula in terms of diameter. So this is 2dl p max by p. Okay. So this is 2dl. So this is 2dl b max by p. Okay. P max 2dl B max by P, na? So here, if you place this 2dl B max by P, so what you are getting? This is 0.1, 2 into zero point 0.5 is 1, so 0.048 only we are getting. Okay, so I don't know what has been done here. I don't know, but this is what has been discussed in the SARS lecture. Okay, so you can follow this. You can take this formula of flux per pole. ठीक है? So, is there any doubt till now? Till this question? These are very like the so theory things I discussed just so that you can know what all sir has discussed, and that you can get some idea about it. Like it's very, it's not exactly the exact detail with which sir has discussed, because sir has like discussed these things in what, like around around 9 10 lectures of half an hour each. So you can understand like it is how much time, right? But here I'm trying to do this in with like I discuss these things within 1 hour or something. So naturally I have not discussed it with that much detail, but I have discussed the important things. Okay, so if you want, you can see these derivations of this pitch factor and distribution factor also. I have not discussed the derivation, I have just given you the formula directly, because the formula only directly will be asked. Okay, so that is why so this formula of distribution factor I have given. Pitch factor also I will give it to you. Okay. So this is the pitch factor formula. Okay. After this only the pitch factor is there. Okay. So why this below thing is not coming? Okay. So let me just open it again. Save. Mm, hmm. So pitch factor formula is this. So let me just write it down. Okay. So here only I'm writing the pitch factor also. Hmm. So pitch factor is equal to cos alpha beta by 2, where alpha is the number of slots which are missed due to short corded coils. So in this example, we have missed, because see, in full pitch coils we have like how many number of coils? 9 number of coils, but we are missing the connection by 2 coils, right? 2 numbers. So instead of 10, we are having 8. So like that, we are missing 2 numbers. So that is why, because we are missing the 2 numbers, that is why this here in place of alpha we have to place 2. Beta we have already found, so here we can just place in this formula. So here you see. So this formula was cos, okay, and alpha beta by 2, where this alpha is the coils which we have missed due to short cording. So here we have missed 2 coils. So 2 into beta, alpha beta is 2 into beta, which is 40 degrees. And here we have to just place it as cos into 40 by 2, which is this much of pitch factor. Okay. These are just formula based questions. Just you have to know the formula. Now, for the pitch factor for the third harmonic, right? So you will see that in his lecture sir has discussed some things. Okay, you can just go through that lecture, but I'm just writing it down here because I think that much derivation is not required. You just need to remember these formulas. According to me, this is not having any it is having some explanation, some little bit of concept, but theory questions will not come out of it. Okay, so cos alpha beta by 2 for fundamental. Okay. Pitch factor for kth harmonic. Okay. So it will be cos k alpha beta by 2. Okay. For the kth harmonic. So here you can just place this. So everything is same. So alpha beta is 40. So cos alpha beta is 40 and k is 3. So instead of this k, we place 3. So 3 into 40 by 2, we get 0.5. Okay. So here it is asking you distribution factor. So distribution factor also you can find. So here you see there is something called as M, right? In the formula which sir has discussed, this is M, right? So M is the number of coils which are distributed, and what are the coils which are distributed? It is given by uh, slots per pole per phase. Okay, this is also called as M. So those are the things which are distributed in this fashion. Okay, to give you like this. So here you can find the slots per pole for phase. Okay. And you can just feed it in this formula. Sine m beta by 2 by m sine beta by 2. It's just the exact formula. Okay. This is the exact sine m beta by 2 by m sine beta by 2, where beta you have to put electrical. Okay. You can put mechanical also, because if you put sine mechanical and divided by sine mechanical, so that will give you some same factor only. Okay. So you need not worry, but you just put it electrical because it is easy to calculate it in electrical directly. So sine m beta by 2 by m sine beta by 2 you can do to get the distribution factor. Okay. So again the distribution factor for the third harmonic. So distribution factor for the third harmonic, what will happen is this, so it will become like this. Okay. So I'm just writing it here. Distribution factor for kth harmonic. Okay. M is slots per pole per phase. Beta is slot pitch. Okay. K is the harmonic number. So here it becomes sine m beta by 2 into k by m sine beta by 2 into k. Okay. So here you just have to place this. So instead of k, you, because this is third harmonic, so m is slots per pole for phase, which is 3. Beta we have found as 20 degree, and k is 3. Okay, because this is the third harmonic. So you just have to feed in the formula to get this. Okay. Now here you have to find the RMS value of EMF which is generated per coil group. Okay. So actually I have little bit doubt in this question, because see, this is the formula of the EMF, but in the formula of EMF you have root 2 pi, you have flux per pole which you have obtained from this question as 48 milliwebers which we have found. Okay. And then you have frequency which is 60 hertz. 6 is the, what you say, 6 turns each, coils have 6 turns each, so for that you have 6. Okay. And what is this 3? I'm not getting. Okay. Instead of other than that, all these things are already known, kp kd value, but what is this 3? I'm not very clear on. So I'll, so for this part I don't know, but other than that everything is known to us. Okay. So what will happen is, because of the pitch factor and distribution factor, the EMF will not be exactly root 2 pi phi n pi phi 5 fn, but it will be having also kp and kd, distribution factor and pitch factor. So distribution factor and pitch factor also we have to multiply. But what is this 3? I'm not getting yet. Okay, so I'll just explain this maybe in the next class, that what is this 3. Okay. So, so that is it for today's class. Today's class, I discussed many things. So here in these questions, these you have to just remember the formula. Okay. And the concepts I have discussed, some of the concepts which I was unable to discuss in the assignment 2, I have discussed, I think till around here. And then assignment 3 onwards, these are the things which have been discussed. Okay. So that is it for today's class. So I'll be sharing this slide and I'll be also uploading the recorded lecture. Okay. So so that is it. So I'll be stopping my class here today. If you have any doubt, you can ask. Otherwise, I'm stopping the lecture here.
Thank you, Sakshi. It was really informative. Only point is that how do we remember all these formulas?
Yes, yes, yes.
Very
Uh,
tricky. Like we need to either memorize or keep it handy.
Yes, yes. Actually, this is how it is. Actually, this assignment, specifically this assignment 3, it has little bit formulas because of this distribution factor, pitch factor, and all these things. But that is what we do not have any other choice, right? We just have to remember to solve this. So that is it. Okay.
Thank you.
Okay, okay then. So I'm stopping the lecture here today. So I'll be sharing this assignment 3 and the recorded lecture also in case you want to revise it again. Okay.
You will be uploading it in NPTEL website or via email?
So what will happen is that here, this NPTEL people, they would have shared with you this Google Drive link. Okay.
Yeah.
So in this Google Drive link, if you go inside, so you will see that every week I am uploading some recorded video lecture on YouTube thing. In this presentation folder link, you will find the, what you say, all the this assignment slides. Okay. Okay. Okay then. So I'm stopping the lecture here today. So that is it. Thank you then. Okay. So I'm stopping the presentation. Okay then. So I'm leaving. Okay. You can also leave. Okay. Okay then. Hmm.